On screen, we have the divided differences table for the function y equals the logarithm of x base 2. The graph of the function is also provided. The divided differences table is constructed out of the points on the function at x equals 0.5, 1, 2, 4, 8, 8 times the square root of 2, and 16. The only reason we are using these points is that the y-coordinates of these points are exact. That is, the base 2 logarithms of the x-coordinates are all exact, and we'll leave that as an easy pre-calculus exercise for the viewer to verify. A point on the graph where the base 2 logarithm is not exact or is irrational is at x equals 10. In this exercise, we will estimate the base 2 logarithm of 10 using various divided differences polynomials that we can obtain from the table. We will describe each polynomial and differentiate each one from the others regarding the accuracy and the behavior of the polynomial in relation to the function y equals the base 2 logarithm of x. A first choice for a polynomial, and an obvious one at that, is the one that uses all the points that are used to construct the table. For this polynomial, since the starting x value is x equals 0.5 and x equals 0.5 corresponds to I equals 0, we use the entries in the first row of the table to construct the polynomial. We call this polynomial p sub 1 of x. It is the Lagrangian polynomial for all the points shown on the table. It just takes on a different form where we use the entries in the divided differences table to construct the polynomial. The first term for p sub 1 of x is minus 1, the y value at x equals 0.5. This is followed by 2, the second entry in the first row. But we have to multiply 2 by the quantity x minus 0.5, 0.5 being the first x value for this row. Then we have minus 0.6667, the third entry. We multiply this by x minus 0.5 and x minus 1. We include the second x-coordinate. We progress along the first row so that the next constant is 0.1429. And this is multiplied by x minus 0.5, x minus 1, and x minus 2. Do you see a pattern? You should be able to guess what the next term should be. It starts with minus 0.0167, and then multiplied by x minus 0.5, x minus 1, and then x minus 2, and then x minus 4. Then we have 0.0014 multiplied by x minus 0.5, x minus 1, x minus 2, x minus 4, and x minus 8. With only one more term in the row, there should be one more term for the polynomial, and it starts out with minus 0.0001 multiplied by x minus 0.5, x minus 1, x minus 2, x minus 4, x minus 8, x minus 8 times the square root of 2. Observe that we do not use x minus 16. To see how well p sub 1 of x approximates the logarithm of x base 2, here is the graph of p sub 1. The section of the polynomial from the left endpoint to the right endpoint is this section, with p sub 1 of 10 marked by the red dot. The base 2 logarithm of 10 is 3.3219 up to 4 decimal places. The value of p sub 1 of 10 as an approximator is 2.7936. This estimate gives us a relative error of 16.4%. This tells us that p sub 1 of 10 is not a particularly good approximation for the base 2 logarithm of 10. A reason for the value of the relative error might be because the interval that we used for p sub 1 is rather large. On an added note, nothing to do with p sub 1 of 10 as an estimate for the base 2 logarithm of 10. Note how badly p sub 1 approximates the base 2 logarithm of x at this portion. It's not quite as bad near the center. The second polynomial, and there will be 5 of these, will use the points from 0.5 to 8 times the square root of 2. The starting x value is still x equals 0.5, so we will use the first row again to generate this polynomial. But because x equals 16 is not included for this polynomial, we have to exclude this constant in the polynomial. This means that in relation to p sub 1, we remove this last term of factors from p sub 1 to get the new polynomial. We'll rename the polynomial. Let's call it p sub 2. Here is the graph of p sub 2, with the segment covering the points that we used to derive p sub 2. We observe a rather pronounced separation between p sub 2 and the graph of the base 2 logarithm of x right here, which is close to the right endpoint. It's similar to what we had observed with p sub 1. Unfortunately, it is also around this interval where x equals 10 is located. One can check that p sub 2 of 10 is approximately 1.8729. The relative error for this estimate is 43.6%. which makes this estimate a worse estimate than the one that we obtained from p sub 1. The main reason could be that x equals 10 is closer to one of the endpoints of the interval. For the third polynomial, we use the points from x equals 0.5 to x equals 8. This is a more extreme case compared to the previous two polynomials because now x equals 10 is actually outside the interval of the points that we will use for the polynomial. Since x equals 0.5 is the left endpoint for this polynomial, we will still be using the entries in the first row. A big difference now with x equals 10 beyond the right endpoint x equals 8 for the interval. We will be extrapolating the base 2 logarithm of 10 using this polynomial. Recall that p sub 2 was 1 point short of p sub 1, and so we excluded this constant from p sub 1 for p sub 2. Similarly, the next polynomial will be 1 point short compared to p sub 2, and so we exclude an additional constant for the new polynomial. The result is that we delete this string of factors from p sub 2 to get the new polynomial. We'll also rename the polynomial. We'll call it p sub 3. Here is the graph of p sub 3, with the segment for the points that we use for p sub 3 highlighted. P sub 3 of 10 is minus 9.6857, which is way down below out of the field of view. It is such a bad estimate for the base 2 logarithm of 10 that we are not even going to find the relative error for this estimate. For the last two estimates, x equals 10 was either outside the interval for the polynomial that we used or very close to one of the endpoints for the polynomial that we constructed. The resulting estimates ended up being no better than the first estimate that we had obtained. The second polynomial used the points from x equals 0.5 through 8 times the square root of 2. For the fourth polynomial, x equals 10 will still be close to the right endpoint for the set of points that we will use, but this time around we will shorten the interval by deleting x equals 0.5 from the points that we will use. This time x equals 1 is the starting left value for the polynomial, and so we will use the second row to generate the polynomial. The polynomial, which we call p sub 4 of x, starts with the y-coordinate of x equals 1, which is y equals 0. This is followed by 1 times the quantity x minus 1. The factor x minus 1 is there because we are starting the points at x equals 1. Then we have minus 0.1667 multiplied by x minus 1 and x minus 2. Then we have 0.0179 times x minus 1, x minus 2, and x minus 4. Then we have minus 0.0014 times x minus 1, x minus 2, x minus 4, and x minus 8. X equals 8 is the second to the last x value, and so this is as far as we go with p sub 4. Here is the graph of p sub 4 with the segment between the points that we used highlighted. The point corresponding to p sub 4 of 10 is indicated by the red dot, and note how close it is to the corresponding point on the graph of the logarithm of x base 2. P sub 4 of 10 is equal to 3.4712, and this gives us an absolute relative error of 4.5%, which is an improvement over all the other estimates that we have obtained so far. For the last polynomial, we will use the points from x equals 2 to x equals 16. This is a fairly long interval, but at least x equals 10 is somewhat centered on the interval. X equals 2 is the leftmost point for this set of points, and so we will use the third row of the table to generate the polynomial. The polynomial, which we call p sub 5, starts with 1. Then we have 0.5 multiplied by x minus 2. Then it's minus 0.0417 multiplied by x minus 2 and x minus 4. Then it's 0.003 multiplied by x minus 2, x minus 4, and x minus 8. And finally, we have minus 0.0002 multiplied by x minus 2, x minus 4, x minus 8, and x minus 8 times the square root of 2. This is what the graph of p sub 5 looks like, with the segment involving the points highlighted. And note how much closer p sub 5 of 10 is to the logarithm of 10 base 2. In fact, they seem to coincide. P sub 5 of 10 is 3.311, and this gives us an absolute relative error of 0.34%. So p sub 5 of 10 is clearly the best estimate that we've obtained so far.